Let's be honest, statistics and data modeling can feel overwhelming. You've got a data set, you've got a research question, but the moment you sit down to analyze, you ask yourself, wait, is this a t-test, a chi-square, regression, something else? And you can't quite put the pieces together. That's exactly why we built this method, to take the guesswork out of method selection. This visual guide is your roadmap for choosing the right statistical method based entirely on your research goal, data structure, and variable types. In this video, I'm going to walk you through how to use it step by step and then dive into tons of real-world examples to show it in action, going from here, from start to finish. Welcome to your guided walkthrough of the method map, a visual and practical tool designed to help you select the right statistical method for your analysis. This tool answers one of the most common and critical questions in analytics and research. What method should I use given my research goal and data requirements? This map leads with your research goal, noted at the top of each block of methods, and leads you through a decision tree based on a few items, most notably the number and type of variables you have, the structure of your data, or the statistical question you're asking. Let's walk through this map and how to use it step by step. Step 1. Start with your analytical goal. At the very top of the method map, you'll see a list of analysis goals or analytics goals. These serve as the foundation for your method choice. Ask yourself, what's the purpose of your analysis? Are you trying to summarize or describe the data? If so, choose describing or summarizing data in the top block. Are we creating visuals to explore or present the data? If so, choose visualizing data. Do we have a hypothesis we want to test? Do we want to make a comparison or run some inference? Choose testing a hypothesis or making inferences. But here we have two branches to choose from. The first one being whether we are testing against a value, a known value, or a hypothesized value. The second, whether we are comparing groups. Let's say we want to examine relationships between variables. Here we would choose understanding relationships. If our goal is to combine variables or cases, which means we are utilizing classification or clustering or reducing dimensions, we go to grouping cases or variables. Maybe we get a little more detailed to decide we want to model cause and effect or explore structural relationships. This leads us to choose modeling cause and effect. And going in an even more granular level, let's say we want to build a predictive model for accuracy, which means to get at a deeper level than some other models in play. If we do, we choose maximizing predictive accuracy. And if we know we are working with time-based data, then we would choose analyzing time-dependent data. Let's take a quick example before moving forward. If your goal is to test whether students who live on campus outperform those that live off campus, performance is the measure of GPA. That's a hypothesis test, comparing two groups, so you'd follow the testing hypothesis branch. And in doing so, we would have a continuous outcome, which is GPA, and a categorical variable with two independent groups. We would then evaluate our sample size, but would likely land on an independent samples t-test. Let's move forward from here. Step 2, identify the type and number of variables. Once you've picked a goal, the next set of decisions involves your variables. Ask, how many variables are involved? 1, 2, or more? What type is each variable? Is it categorical, like gender, yes, no, or the major selected? Or is it continuous, like GPA, income, or height? The method map will walk you through these choices with branches like the following. A single variable that is categorical, and we want to know the center point estimate. In doing so, we would select the mode. Let's say we have two or multiple variables that are categorical as well as continuous. In doing so, we would use violin plot or string plot. Let's say we go to multiple variables and these variables are categorical. We might choose to go to cross-tabulation and from there, go to chi-square test. You're not picking a method out of a hat. You're matching your data structure to the appropriate tool. If your goal is inference, comparing means, proportions, or distributions, the method map has a whole section dedicated to it. Ask, are you comparing to a known value, or are you comparing groups? Say we know we are comparing groups. Is your outcome variable continuous, or is your outcome variable categorical? Now from here, how many groups are you comparing? Are you comparing unique groups or one group at different times? Are your samples independent or related, like having a time component involved? Once we determine whether we are, 1, looking to compare to something known or hypothesized value, Or 2, we're looking to compare groups, we would then follow the appropriate branch. So now let's say we have one continuous outcome. Do we want to compare 2 groups? If so, we use independent samples t-test. What about more than 2 groups? Then we select one-way ANOVA. How about one group at 2 time points? We use pair samples t-test. And maybe more than 2 time points. Here we would utilize repeated measures ANOVA. Now let's move over to categorical outcomes. Let's say we want to compare 2 proportions. We would use a 2 proportion z-test. Say we want to compare groups on category counts. This suggests chi-square test of independence. But if we have one group versus an expected count or a given distribution that we know or hypothesize, but not groups, then here we would go to a completely different block and identify that we would use the chi-square goodness of fit test. Now let's assume that we're examining associations or relationships instead of differences. We would opt for this unique block of methods. If you have 2 continuous variables, notably when there is no clear outcome or target variable, we would choose Pearson correlation. But if you have one continuous outcome and multiple predictors, and the outcome is clear, not uncertain, we go to linear regression. But now let's say that outcome is binary, like for example, an individual is hired or not. We opt for logistic regression, as it is a binary target outcome. This section itself helps you predict or explain one variable using others. Now let's assume your goal is to combine cases or variables, which means we are utilizing classification or clustering or reducing dimensions. We would move to this section. Let's say we want to group people or cases based on patterns. Do we have all numeric variables? We would opt for k-means clustering. But if we have mixed data types, hierarchical clustering is likely better. But now, if we want to reduce dimensionality or do data reduction through grouping variables, we would opt to use principal component analysis, PCA, or factor analysis, FA. Now to more complex relationships, like looking at cause and effect, paths, mediators, or some level of hierarchy. Here we would use path analysis or structural equation model. But we would use multi-level modeling for nested data. If your focus is solely on prediction, notably predictive accuracy, and less so explanation, and we want to maximize how accurate our predictions might be, we go to the bottom middle section. Let's say we have a binary outcome. Our best choice and easiest choice might be to use logistic regression, but truth be told, any outcome type, and it then becomes about your data structure. We can use decision trees, support vector machine, or random forest, and the remaining depends on your data structure and, honestly, comparing performances across all model types. But what if we have a continuous outcome? We might use linear regression, tree models, or neural networks. But if we have a lot of predictors, maybe consider regularization or tree-based models. If your data is time-based, and let's say we want to identify patterns about that time, we would utilize seasonal decomposition. What if we want to forecast future values? We would look at ARIMA, whole winters, or exponential smoothing. But what if we have multiple time series? This is where we might utilize vector autoregression, VAR. This method map gives you a structured, question-driven way to choose a method that matches your goal, fits your data structure, and meets the assumptions of the method. It doesn't just suggest tests, it teaches why they're appropriate. Use it as a decision tree, a teaching aid, or a checklist before you run your analysis. With this guide, you'll be more confident in your method selection and more credible in your results. This map is designed to help you think like a curious modeler. Start with your research goal, follow the structure of your data, land on a method that makes sense, statistically and practically. It's perfect for students, researchers, analysts, and even faculty teaching stats. Whether you're designing a study or analyzing results, this tree keeps you grounded and efficient. Now that you know how to navigate the method math, let's put it into practice. From here on out, we'll walk through a series of end-to-end examples, starting with a real question, identifying the goal, classifying the data, and following the map to the correct method, then executing from that decision. You'll see exactly how to go from confusion to confidence, one decision point at a time. Let's dive in.